Hello everyone, welcome back to this course on reinforced concrete design. We are in week 5 and this is our third lecture. So what we have learned is column design, and in this series of lectures this week we have learned column design for axial compression and uniaxial bending, right? And if you recall, we have learned for a given section how to find out the sectional capacity, that is Pu and Mu, right? Now we have also derived expressions for these two force components for different locations of XU. Recall, XU is equal to infinite. That means we had minimum amount of eccentricity, then XU greater than equal to D and XU less than D, where D is the sectional depth, right? So with that background, let us solve some example today and let us see how we can use the theory that we have developed for the design of columns. Now, the first problem today we are going to solve is here. So, example 1. We have a 300 by 500 column, and this column is having 6 25 bars, and the force is applied here, which is Pu, and the distance from this center of the column to this force is the eccentricity, right? Now this distance from the surface of the column to the center line is given, so this is 60 millimeter. So it includes clear cover plus half the diameter of the bar, so that is given. This problem also mentions neutral axis. As you can see, in actual design problem we need to find out the location of this neutral axis, right? So that we'll see later. We have to solve it iteratively, but for this problem this location is given, and here the strain is 0.0035. Now we have 3 layers of steel, so for that we have epsilon 1, then epsilon 2, and then we have epsilon 3. In addition to that, we have the location where we have to have parabolic profile, so there we have 0.002 strain, and the stress here is 0.446 FCK. So the compressive force from concrete, we get it here, that passes through the CG of this stress block, having parabolic initially and then rectangular as per codal provisions. So the strain diagram is shown, and here we have stress diagram. We have 3 layers of steel, so for each layer we have forces, right? Now the column is made of M30 concrete and Fe 415 bars. Our task is to find the design strength corresponding to balanced failure. Recall we talked about 3 different types of failure. So for this problem, we have balanced failure. Now for this problem, again, we have already drawn this strain and stress diagram. Our task is to find out the design strength. So FCK for this problem is 30 Newton per millimeter square and Fy is equal to 415 Newton per millimeter square. Then let us find out the steel in each layer. AS1 is equal to AS2 is equal to AS3 is pi by 4 into 25 square into 2, that is 981 millimeter square. Now for each layer we can also find out the location. So Y1, that's the first layer here. So this is the first layer, this is the second layer, and the third layer is here. So for the first layer, the location is in the negative direction. So if this is positive X or say Y, Y1 is 250 minus 60. So this is minus 190 millimeter. Y2 is 0 because it is exactly on the centroidal axis, and then Y3 is equal to plus 190 millimeter. So with that background, let us start the design, right? So for that, let us go to step 1. Remember, we identified different steps. For this problem, the first step is to identify strains in different layers. Normally, we first find out XU. For that, if you recall the steps we discussed, we start with an assumed value of XU and then we iteratively solve. But in this problem, we have XU for balanced section. So for this problem, the concrete will have a strain of 0035 and we can actually use this notation for strain. So the strain in first layer of steel is 0.002 plus 0.87 Fy divided by Es. We have Fe415, so for that this strain is 0.0038. Now, if you go back to the strain diagram, we know epsilon 1. We know the strain in the extreme compression fiber. So we can figure out XU, which is for the balance section, we have 500 minus 60 divided by 0.0035 plus 0.0038 times 0.0035. So you get it from this strain diagram, and the value is 210 millimeter. Now recall, XU limit for this balance section is 0.479D if the steel is Fe415 and this is 210 millimeter. So we have identified the location of neutral axis for this given problem. Now our task is to go to the next step, and in the next step, once we identify the neutral axis, is to find out strain in different layers of steels. So the first layer, where we have tension, as you can see, it is the other side of the neutral axis. So for this one, we have epsilon 1 is equal to minus 0.0038. This we have already identified. And this negative value is for tensile. So let us mark it. Now for epsilon 2, again, let us go back to the strain diagram. And we know the location of these two different layers of steel. So from this diagram, we can easily find out epsilon 2. And if you do that, you have again minus, that is the tension zone, 0.0038 divided by 210, then multiplied by 250 minus 60. So this value is minus 0.0000648. Again, this is tensile. Third one, epsilon 3, which is on the other side, it is under compression, you can see here. And from that diagram, again, we can find out, it's not a problem. So it is 0.0035 divided by 210 times 210 minus 60. So this is 0.002504 and this is compressive. Now note, this value is epsilon 3 is more than 0.002. So from this information, we can easily find out if S1, and for that, we need to refer the stress strain diagram, and you can see this is the stress strain diagram for steel, and we have a similar diagram for different grades of steel, and we can easily find out corresponding to strain value the exact value of stress, right? And depending upon yielding, we need to see whether we are in the linear part or we have to read the stress beyond the yielding point, right? So for the first one, again, we have minus Fy divided by 1.15, that is 0.87 if you recall. So this is 361 Newton per millimeter square. Similarly, if S2, but this time it is in the linear zone, so we have epsilon 2 times E of S, and for this one it is minus 129.6 Newton per millimeter square. Then finally, if S3 corresponding to this value of strain, which is again more than 0.002, and the value is 345.2 Newton per millimeter square. Right. Okay. Now once that is done, next step, we have to find out FC3, because this third layer here the moment we find out its contribution, FUS3, we have to figure out the stress in the steel bar and the stress in the concrete surrounding the steel bar, right? So let us do that exercise. So FS3 in this case, again, it is 0.446 FCK, because we are in the rectangular stress block. Here you can see, and that's the reason here we have this value of compressive stress. So now for M30 concrete, this is 13.38 Newton per. Now here you may note that FC1 and FC2 we are neglected. Why? Because they are in the tension zone, and in tension we have very small contribution from concrete, and that's why for the steels in the tension zone we neglect FCI values, right? Okay, so now step 4, we have to find out the axial capacity, and for that, if you recall the expression, 0.36 FCK K times BD plus summation I equal to 1 to N FSI minus FCI times ASI. So let us put the values. 0.36 into 30 into K is 210 times 300 times 500 plus we have 3 layers of steels. So for the first layer, the stress in the steel is minus 361. So we have here minus 361 minus 0 because we neglect FC1, plus we have second layer having a stress of minus 129.6. So it is minus 129.6 minus 0 plus then the third layer having 345.2. So 345.2 minus, for this layer we have concrete, so which is 13.38. All this will be multiplied by 981, that is the area of the steel in each layer. So finally what we get, if you solve this, for the first part we have 680 400 plus this third bracketed term multiplied by 981 will give us 156351. So total capacity is 524049 Newton. So that means PU is equal to 524 kilonewton. So the first question is answered. Next is the moment capacity. For the moment capacity again, MU is equal to MUC plus MUS. So first find out MUC, which is equal to PUC, that we have already evaluated, times 0.5D minus 0.416 XU. So PUC, if you recall, it was 680,400 times 0.5 times 500 minus 0.416 times 210. So ultimately we get 110.66 into 10 to the power 6 Newton millimeter. So effectively we have 110 kilonewton. Now let us also find out the contribution from steel, and for that we have 3 layers. So I equal to 1 to 3, and then P U S I times Yi. Recall Yi we have already identified here, so we know the locations of each layer of steel, and now we can identify the contribution of steel in the moment capacity, right? So for that, again, we have 3 layers. For the first layer, we have minus 361. If you recall, that's the stress in the first layer of steel multiplied by its location, which is Y1 equal to minus 190. Okay, so this multiplied by minus 190 plus for the second layer, stress is 129.6. So let us take minus 130. We can take the exact value. It will not cause any significant difference. Multiplied by Yi 0. Plus for the last layer, we have 345.2 we can also neglect, minus we have 13.38 times we have the location 190. All this will be multiplied by the area of steel in each layer, that is 981. So if you solve this, you'll get 129.13 into 10 to the power 6 Newton millimeter. So that means 129 kilonewton meter. So mu, that is the moment capacity of the section, is the summation of the two components 110 and 129. So this is effectively 239 kilonewton meter. Now then finally we can also check the eccentricity. So let us see the eccentricity E, which is mu divided by pu. So we have here 239 divided by 524, which is equal to 0.456 millimeter. Sorry, meter. So in millimeter it is 456 millimeter. Now E by D, let us check. So E by D is 456 divided by 500. So it is equal to 0.91. And K we have already evaluated. K is nothing but 210 divided by 500, which is equal to 0.42. So this is the combination for balanced failure. So if you have tension failure, we can easily identify the condition. For that, E by D is to be greater than 0.91 and K must be less than 0.42. And for compression failure, it is the opposite. So it will have E by D less than 0.91 and K greater than 0.4. So it solves the complete problem. As you can see, we can identify the sectional capacity for this column under axial compression and uniaxial bending. Now, again I go back to this stress strain curve. These are available in SP16. Recall we discussed this earlier. This is a design aid to IS 456, and there are different design charts and tables provided in this codal provision, and then actually we can use this to find out the stress corresponding to different values of strain, right? There are also sometimes different design tables are available. You can actually have this plots in tabular form, that also you can use, and in between two values of strain you can interpolate and find out the exact value of stress. So that's a standard procedure you follow. Nevertheless, this example gives you an idea how we are going to design a column under axial compression and uniaxial bend. So now let us go to a second problem, because in this problem we did not locate the neutral axis. For the second problem, what we do, we consider again the same configuration. For this problem, determine mu for pure fracture, that is Pu is equal to 0. So is the same section. We have 6, 25 5 bar, and we use M30 concrete and Fe415 bars. This distance, this is 60, and again we have epsilon 1, epsilon 2, and then epsilon 3. This value of strain is 0.0035, and then you have PUS1, PUS2, PUS3, and then PUC. Okay, so for this problem, AS1 is equal to AS2 is equal to AS3, 981 millimeter square. And recall Y1 is equal to minus 190 millimeter, Y2 is 0, and Y3 is equal to plus 190 millimeter. Now here we do not have that balance condition that we use to locate the neutral axis, which is shown here. So for this problem, we first have to figure out the neutral axis, right? So let us start our iteration. So let us start with neutral axis located at the extreme edge. So for this condition, step 1, we have epsilon 1 is greater than 0.002 plus 0.87 Fy divided by Es. That means it is greater than 0.0038. So first we assume 3/7 XU is greater than equal to 60. It gives XU, this is the initial guess, is 140 millimeter. Obviously this is not the value. We'll see how we can iterate it. Now our next task is to find out epsilon 2, which is again from the strain diagram. We can find out now the same way we did earlier. So 250 by 140 minus 1, and this value is 0.00275. Epsilon 3 is equal to again 0.0035 times XU minimum minus 60 divided by XU minimum. So this is equal to 0.0035 1 minus 60 divided by XU minimum. We are not going to put this value of XU here. I will see in a minute how we are going to find out iteratively. So epsilon 3, now the stresses, we have Fs1, we know epsilon 1, so Fs1 is 0.87 Fy because the strain is more than 0.0038. So this is equal to 361 Newton per millimeter square. Similarly, Fs2 is corresponding to this value of strain. So we have to go back to that diagram here, and from that we have to figure out the strain. So if you do that, Fs2 is 351.7 Newton per millimeter square. Now for Fs3, which is in the compression zone, E times epsilon, so 0.0035 times 1 minus 60 divided by XU minimum times 2 into 10 to the power 5. So this is equal to 700 minus 42,000 divided by XU minimum. Now FC1 is 0 because that is the tensile region. FC2 is equal to 0. FC3 is equal to 0.446 FCK, which is equal to 13.38 Newton per millimeter square. Okay, now we go to step 2. Here what we do, we equate total compressive force and total tensile force because we have to solve the location of the neutral axis, right? So total compressive force is equal to 0.36 FCK B times XU minimum plus 700 minus 42,000 by XU minimum minus, recall the stress in concrete is 13.8 times 981. So this is equal to 3240 XU minimum plus 700 minus 42,000 divided by XU minimum minus 13.38 times 981. Then total tensile force is equal to Fs1 plus Fs2 times S. So this is 361 plus 351.7 times 981. So this is equal to 699,595 Newton. Now we can equate these two. So we have 3240 XU minimum plus 700 minus 42,000 divided by XU minimum minus 13.38 times 981 is equal to 699,595 595. Now you can see this is a quadratic equation of XU min. If you simplify this, you will get the quadratic equation as 3.3 XU minimum square minus 26.52 XU minimum minus 42,000 is equal to 0. So if you solve for XU minimum, you will get 116.85 millimeter. Now this value is based on the assumption we started with, the first assumption, that is XU equal to 140. So now after first iteration, we get this value. So then what we do, we have to iterate again. So now the iteration starts. So step 3, we assume XU minimum to be 116.85. So let us start with 117 millimeter. And then you can repeat the same exercise. Let me just leave it for you. So you have to find out epsilon 1, epsilon 2, epsilon 3, corresponding FS1, FS2, FS3, and obviously FC1 equal to 0, FC2 equal to 0, and FC3 you have to find out. This is 0.446 times FCK. Now based on that, again you have to develop the same equation where you have to find out total compressive force, total tensile force, and then equate them. You will again find out another value of XU minimum. And if you repeat that exercise after second iteration, you will see you will get XU minimum is 118 millimeter, but still not converged. Okay. So you have to continue that iteration until it converges, and once it converges, the remaining part is straightforward because we have to find out the capacity of the section. Now with this value, let us assume that this value is the final value of XU min, which is not. That I leave it for you to complete the exercise. So for the converged value, if you do it, you will see what you expect. You expect in the next step, step 4, PU, and PU value will be 0 because that is the main target. So we have to get it, and then MU, right? But for the time being, let us solve for both of them and let us see after this second iteration what is the value of PU. So PU is 0.36 times 30 times 300 times, we use this 118 as our XU, so that is the value, and then we have to get the contribution from steel. So for that, the first one, if you repeat, we have minus 361 times 981. Then this is from the first layer plus, let us use that value of Fs, what we did earlier, which is not exact because you have to figure out after this convergence, you have to again figure out epsilon 1, epsilon 2, epsilon 3 and corresponding stresses. So because it is close, let us use this old values and let us just cross verify. Leave that exercise for you. Exactly you have to find out the value. So this is 351.7. So we have minus 351.7 times 981 plus we have 306 minus 13.38 times 981. So if you do that, you'll see it is not exactly 0 because we are yet to get this XU converged and appropriate values of stresses. So you'll get something like 42 kilonewton, which is not 0. So that task I leave it as a exercise for you, home task. So you will first complete the iteration, find out the converged value of XU, and then again go back to the strain diagram, identify the strains at 3 different layers and find out the sectional capacity. So obviously this is not equal to 0, so this result has not yet converged. So that exercise please complete. If you have any difficulty, do let us know, we will help you out. Now let us quickly complete the remaining part. So that is moment. We will have contribution from steel and concrete. So for concrete, this is the force times the lever arm, which is 440 minus 0.416 times this 118 is the lever arm, plus we have 3 different layers. Out of that, one layer is at the middle, so minus 361.981 times 440 minus 250. So this is for the first layer. Let us go back to the figure. So this is the first layer, this is the second layer, and this is the third layer. So for the first layer, we have, from this face we can identify the location, and then we can identify from this point. Okay. Plus we have another layer which is 306 minus 13.38 times 981 times 440 minus 60. So if you solve this, you will ultimately get 122.87 kilonewton meter. So that is the sectional capacity. Now again I repeat, this is not the converged value because we are yet to complete the iteration. That exercise you complete, but again at the end of converged XU value, you can easily find out the PU and MU using the expression that we have already derived, right? So with this example, you see how to solve the capacity for a column which is under axial compression and uniaxial bending. We'll have some more examples given in your exercise. So you just solve them. If you have any difficulty, do let us know and we will help you out. Now, the last part of column design is when we have the column with biaxial bending. So that we actually cover at the end of this course, because by then you will also come to know how to solve this problem under uniaxial bending and you will be comfortable. Then we will consider, and also that time in the last week we will show some advanced design, and there we will show how to use the interaction curves. Now before we close here, let me show you the interaction curves that are provided in SP16. As you can see here, these are the interaction curves, and here you can see it is PU divided by FCK BD, and here in the x-axis you have MU by FCK BD square. Remember, we derived these expressions earlier in the previous lecture, and from this plot actually you can find out the sectional capacity. So for this particular section, and the amount of steel and the quality of steel is given here. For that, this interaction diagram is given. So you can easily use this diagram to do the design. So that we'll cover, not now. We always recommend you go by analytical methods where you use equations to derive the sectional capacity. But as a designer, you should know how to use these interaction curves that we'll do at the end. And using this interaction curve, very easily you can actually identify the sectional capacity. So for different category of steels, these curves for different geometry and these different configurations, these curves are given in SP 16, which is a design aid to IS 456. So there you will get all this stress strain diagram tables and this kind of interactions charts, right? But again, I will recommend you just follow the analytical method, use equations, solve each and every step, because that will give you confidence. And then once you are confident, you can use this type of interaction curves to easily design, right? So we have slightly modified our weekly coverage of the syllabus. So next week we will cover foundation design along with ductility detailing, and we'll follow other topic in the following lectures. In the last week, we'll come back and we'll solve some example with biaxial bending, and we'll also learn how to use this interaction curve. With that, let us close here. Go through this notes, and if you have any difficulty, do let us know. Thank you very much.